Hello, everybody. As the slide shows, I work for Apple as Nicolas and other people who are here in the room. And I think I have the shortest title ever of the presentation. I'm sorry, I didn't mean to go there. I want to go back. Shortest title possible, HDR in ICC. I was even wondering if that title needs to be translated to other languages. We have 2 3-letter acronyms that I think are used in all languages that we know. Maybe the word "in" would have to be translated. So, long story short, you already heard about how the HDR content can be captured, can be created, and can be displayed. But I want to talk about one specific aspect of HDR, which is processing of HDR content. You heard from the previous speakers that there are already technology moved us far along, and we can create that content, but in our daily life, we have many devices that cannot match the demand created by HDR content. So this is where the thought was that maybe ICC, again, another acronym, as you know, stands for International Core Consortium, but if we talk about ICC, we don't think about this consortium, we think about the standard that was created and widely adopted, which allows for creating of heterogeneous networks of different devices and for faithful color reproduction. So, okay. Max already presented to you the statement showing how what is the statement, or rather, what is the mission of ICC? So I don't want to spend too much time on it. All what we know that ICC profiles are the basis for creating those heterogeneous color management workflows. And here is an example. I have to, in this scenario, I'm trying to show all variety of different devices that we want to control. And as you see, they are not necessarily all HDR capable. Therefore, we need to create a system which will allow us to manage HDR and represent it on different devices in the best possible way. The ICC concept is based on 2 ideas. One is ICC profile, that describes colorimetry of the device, and another part of that is providing some standardized algorithm which are using a reference color space. Another acronym comes here. We call it also profile connection space. So the idea is that if I can represent the capabilities of the device using a profile, I can use a transform to this reference color space, and from there, using another profile of another device, find a way to provide the best reproduction on the other device. So I'm having problems with moving the slides. Going wrong direction. Okay. So what was the ICC was created many years before the idea of HDR even came around. So the major problem that we are trying to solve by using those ICC profiles was actually just gamma mapping. This is some kind of trivialized drawing showing what are we dealing with, but as you see, some decisions needs to be made how to bring the color being present in one gamut into another. That also implies that if I map many colors to one, going from bigger gamma to smaller, I cannot reproduce it going back. So the choice of the color space is very important. The ICC proposes to use specific algorithmic operations which allow us to create models for different color devices. There are very simple three components. One is tone rendering curve, which can be represented as a one-dimensional LUT with interpolation, and also that tone rendering curve can be represented as a parametric function, but as you see, we kind of, from the beginning, restricted to what at the time was state of the art. We also have a matrix that allows us to combine linearly components, and at the end we have a color LUT, which we for short call CLUT, which is multi-dimensional interpolation table, which allows us to process n inputs and produce m outputs. Okay. Looks like I'm really getting stuck here, I'm sorry. Okay. So those three different basic operations, oh now I went too far. Okay. We can characterize display. Oh my gosh, I'm sorry about this, flipping back and forth. We have two types of typical ICC profiles. One is called matrix-based, which this allows us to characterize the space as a specific transfer function and matrix, which allows us to convert the RGB channels to XYZ. That is then ready for being picked up by another profile to use the same methodology using primaries of the other device and inverted TRCs to encode it for a specific color space. Why this is important? Because there was some talk here about capturing HDR. As you know, a lot of processing is happening in the camera. One could think about just leaving and creating a profile for camera which will represent colorimetry and allow for further processing down the road to happen, understanding how the camera works, but this is not how this stuff comes together. The camera is actually producing images in a, as we call it, output intended color space. As you know, you probably heard about color spaces like sRGB or Adobe RGB and so forth, and all these important color spaces use this matrix TRC color profile to describe the colorimetry of the image. Another more complicated profile is using that interpolation, color interpolation lookup table, multi-dimensional interpolation table that I mentioned, that allows us to do more operations which are related to gamma mapping in a specific way. For example, introduce some perceptual aspects of color management. Most typically, this is where we are dealing with more complicated processes like printer. Then our intent is to reproduce the color the best possible way on this device, and this is where this model which I'm presenting is useful. Oops. So if we think about this original design of ICC, there was, as I mentioned, the main idea was to provide some tools for gamma mapping. The device color is device color gamma is captured under one illuminant. It is important in terms of how we are preparing the data or processing for connecting profiles in profile connection space. Everything is chromatically adapted to D50. But also, it is a specific model in which the operations are kind of anonymous. The profile was designed the way I don't need to know what this function or those prime matrix represents. We know that they are related to specific primaries of the color space and transfer functions. So it is good, but also, on the other hand, does not allow us for easy identification of the specific color space. Therefore, in the industry, many specifications would avoid using directly ICC profile using some signatures, like, for example, EXIF data in JPEG. They just specifying a numerical value, we know that the color space of that image is RGB. The same thing has to do with TRCs, which can be very general. You can think about a lookup table being able to reproduce anything we want, but it's difficult to find out what actually this function represents in terms of standards. And what we now are talking about is dynamic range. There was no provisions in the original ICC profile for that. My previous speakers described to you very well what device dynamic range of is, high dynamic range. So we can talk about this as a kind of contrast ratio, which is the ratio of the darkest color and the brightest color. And using this kind of characterization, we have two groups of devices that you already heard. There is a standard dynamic range and high dynamic range. As you see, significant difference in the range of values that can be processed by those devices. As also was mentioned here, still, even though the high dynamic range devices showed up, they still are not exactly as good as human vision system, but allow us to reproduce that real scenes captured by the cameras in much more realistic way. So this is, I like this picture that allows us to kind of encapsulate the difference between HDR and SDR. As you see, there is a full high dynamic range of human vision, and technology of SDR makes us barely peeking into that range, and we need to use specific techniques which he described to reproduce it in SDR range. As the dynamic range devices showed up, the range is much wider now. However, it's still varying, right? We know that we can tone map from HDR to SDR, but we have, in a specific scenario that ICC tries to address, we want to resolve the problem for many different devices. Therefore, combining now what ICC originally was addressing, which was gamut mapping, with the dynamic range, and that term was mentioned here before, I believe, by Timo, we talk about color volume. So we are not only interested in reproduction color in some small range, but also maintaining our reference white at a certain point, use the remaining part of the color volume for reproducing highlights. Also, those HDR devices have much deeper blacks. That's something that also we want to address. So in terms of managing color volumes, it can be broken into two parts. One would be traditional, the new thing that we want to control through is tone mapping, and that after we are done with tone mapping to bring it to a specific volume, we then worry about gamut mapping color to process the HDR content. Okay, all right. So as was mentioned here, we now have a concept of color volume, and the data needs to be somehow stored and for transmitting, and the purest form, something that Timo mentioned as well, it is unclipped floating point values, could be specified in either scene or display referred color space. However, this is very impractical. Yes, it is possible to be done in OpenEXR or TIFF, but in the world where HDR was adopted first, which was video, that definitely was not the right solution. So through different work in different companies, one in Dolby, one in BBC and AJK, two industry standards for HDR were developed. One is called PQ, and which represents absolute display referred data, and another one, HLG, developed by BBC, as I mentioned, in cooperation with NHK. Nicolas also mentioned that there are still images, HDR, which can be created using the gain map, and the advantage of this model is that if we have a base image which is SDR and we have a separate gain map, the older system which do not understand HDR can use the SDR representation, and the ones that can reproduce HDR can just combine that SDR with HDR and create HDR with gain map and create HDR image. Oops, going wrong directions. So to talk more about processing of HDR content, I would like to, for a second, go back to this description of the mathematical functions which are used for describing the process which is happening in the camera by converting the scene light into a signal that can be processed or stored and passed to another device. That function is known as optoelectrical transfer function, transfers the scene light into a signal. When we want to display the signal, we need to convert this signal to display linear space, which is representative of device capabilities. That both functions combined create what is called OOTF, which is optical transfer function, and that allows us to describe the process of converting from scene linear data to the display light. What is important to know about these functions that I need to know only two to recreate the third one. And here are all the combinations that can be achieved. Never learn which way to go. Why this is important? Because those two standards, which I described to you before, are using different transfer functions. The PQ, the operation of converting scene light to signal is by applying the OOTF and inverse EOTF, and the signal that we receive is already in display referred data, and all what we need to do is then apply this EOTF to convert it to display light. The file will contain this, as I mentioned, encoded display referred data, transfer function, and color primaries, and additional metadata. And as we know, there are the cameras which capture also and store gain maps. Another architecture opposing is actually using OETF and producing the signal which remains as an encoded scene referred data, and the function which is defined is OETF, specifically HLG OETF. So now, in order to convert this signal to display light, I need to, based on the knowledge of OETF, I need to invert it and apply OOTF, which is defined by the spec, so I have the data which is ready to be displayed. So when we think about the different steps that we have to take in order to process the HDR data and make it compatible with the device on which we are trying to display it, first we need to decode it from display light linear, to encode it to display light linear space. Then we need to apply tone mapping. And we want that tone mapping to be parametric, not necessarily. It looks like I'm exceeding the time. ICC, we are looking at specific loop functions, which we call adaptive. They can be created on, for example, from the gain map. Applying that, I can target a specific. Very quickly, how this works. Sorry. So we knew all those processes exist, and we tried to address that in ICC. We created an HDR working group, and which works with standards that were described here by Nicola. This is ISO TC42 and SMPTE, and the result of this work were two new HDR-oriented tags. One is CICP, and another is AGGC. I apologize for acronyms. In a second, I'll try to explain what it is. We also allow for storing ICC HDR metadata in ICC profile. This metadata is registered with ICC. You see some acronyms. I'll go to those in a second. But also what was very important for us, that when we create a new profile describing how to process HDR for a specific target headroom, we also are able to use that with all the CMM, sorry, another acronym. CMM stands for Color Management Module, which understands the profiles and prepares color transforms. So CICP is something which is used in other standards, is a coding independent code points. It is a significant shift from traditional ICC color approach where, as I mentioned, the processing was described by some anonymous matrices and transfer function and lookup tables. Here, CICP instead are using as identifiers, and those can be found in ITU specifications like, for example, ITU Reg H273. This makes a difference for CMMs because now the CMM needs to know how to interpret the primaries of those IDs specified by CICP. And what is important to know that this H273 contains also identifiers for PQ, EOTF, and HLG OTF. So now the profile can say, I am just, so we also came up with the idea of this adaptive gain curve that is a very powerful transfer function, which in essence is a piecewise cubic curve, which allows us to approximate gain maps in one global function. Here are the examples of how this adaptive gain curve looks. I can specify the target headroom that I want to address, and here's a utility on existing MAC, which shows you if I don't do anything, my gain curve maintains the level of gain as is. If I specify curves data that can be maintained. All right, looks like I exceeded the time, so thank you for your attention. And as we make a progress on this,